Welcome to EDU World Space.
So in this question, we are told that we normally have two different equations that we can use for gravitational potential energy of a mass, a small mass in the presence of a larger mass such as the Earth. And we're asked to compare these two formulas and find the point where the approximation, the first one, is an error by 1%. So the point here is that we have one formula that is an exact formula, and we have another formula that is really an approximation, and we want to find that point where that approximation is an error by 1%. So the two formulas that we're referring to in this problem are mgy, and then we also have negative gmm over r. Now, the first thing to notice is that these are potential energies at just a point. What we want to be doing is comparing the change in potential energy over a certain distance and see where that differs by 1%. Because in energies, the absolute numbers really don't mean that much. It's more of the change that we want to be considering. So for this version, we're going to be looking at mg delta y. And for this version, we're going to be looking at negative gmm over rf. So that'll be our final r, minus, which becomes a plus, gmm r E, because I'm going to use my initial position as the radius of the Earth, or the surface of the Earth, I should say. So the difference between RF and RE is actually delta Y, right? Because we're going from the radius of the Earth to a new, slightly bigger radius, and that will give us our change in height. And what I'm going to do is I'm going to set up an equation which has these two changes in potential energies as a ratio, and I can set that equal to a number to find out when that first one is an error by 1%. So I'm going to create this ratio here, mg delta y divided by the second formula here. And what am I going to set that equal to? Well, I know that mg delta y is going to be a slight overestimation because the potential energy is not decreasing as y gets bigger, like it is in the second formula. So basically, if this was a accurate approximation, then this ratio would be equal to 1, but we want a little bit extra. We want that 1%. So we're going to use 1 plus 1%, or 1.01 here. So now we have a ratio which basically says that the first formula is 1% bigger than that second formula on the bottom of the fraction. And just to make this a little bit easier, I'm going to rewrite RF in terms of the radius of the Earth and delta y. So we know that, actually, I'll just erase it here. We know that the final radius is going to be the original radius, which was the radius of the Earth, plus delta y, whatever distance we went up in height. And basically what we need to do now is solve for delta y. So we have a lot of math to do here. So let's get started with that. So first thing I'm going to do is I'm going to multiply both sides by the denominator here to bring it up. So this is going to go here. So I get mg delta y is equal to 1.01, and I'm also going to factor out a gmm here. And so that'll leave 1 over RE minus 1 over RE plus delta Y. And I did reverse the order of the terms there, so the 1 over RE comes first. Next, what we want to do is consolidate this fraction. So we're going to multiply to get a common denominator. So the first fraction, we're going to multiply by RE plus delta Y. So we do need to multiply on both the top and the bottom. And the second fraction, we're going to multiply by RE, both on the top and the bottom. So what does that mean? It means that on the bottom, we're going to have RE times RE plus delta Y. On the top, it'll be RE plus delta Y. And then for this fraction, it'll be RE over RE times RE plus delta Y. So now we have the same denominator. We can put these two together. So I'm just going to rewrite it quickly here. So it's going to be RE plus delta Y. And then it'll be RE plus delta Y minus RE. So the two RE's cancel and we just are left with delta Y. Actually, let me write out the whole thing here so it doesn't get confusing. And we're going to do some cancellations here as well at this point. So you can see here that we have a little m on both sides. We can cancel that out. We also have a delta y on both sides that we can cancel out. And then we can go about continuing to rearrange this. So what do we have left? Let's keep in mind we're still trying to isolate for delta y. So I'm just combining the fractions here. So I've got RE times RE plus delta Y still on the bottom. So I'm going to multiply by the denominator here on both sides. And so I will get 1.01 GM on the right-hand side and G RE. Let me put these two together. So RE squared, I'm just multiplying this in, plus RE delta Y. And we're going to multiply in that little g. And we've almost isolated delta y here. We're getting there. So I'm going to take the GRE squared over to the other side. So that's minus GRE squared. And then we're going to divide everything by GRE. So our final formula for this delta y, which gives a 1% error in MGY, is going to be this on the right-hand side here. Okay, what are all of these numbers? So the G is our regular G. The M is the mass of the Earth, the big body. We're subtracting off 9.81 times the radius of the Earth in meters squared, divided by 9.81 again, times the radius of the Earth, not squared this time. Okay, and once you plug that into a calculator, you should get a final value for delta y of 6.39 times 10 to the 4 meters. Okay, so this is the distance above the Earth where that MGY formula gives a 1% error in what the actual change in potential energy is over that distance. So this is our final answer. We can also quote this in terms of the radius of the Earth, because that was something that was asked for in the question. So we can take this 6.39 times 10 to the 4 and divide by the radius of the Earth. And it happens to be about 1% of the Earth's radius. So this will give 0.01, which means 1% of the Earth's radius. And that is our final answer.